everyone. Today we will learn Chapter 2, Signal Processing in Time Domain. In this chapter, we will learn elementary signals, basic operations, and signal decomposition. For elementary signals, we will emphasize on the definition, characteristic, and their relationship. You should pay attention to the differences and similarities between the continuous time domain signals and the discrete time domain signals. For basic operations, we will emphasize on the mathematical and physical concepts. Now let's have a discussion. In general, most signals are not elementary signals. Why do we have to start from analyzing the elementary signals? Here are two reasons. One is that any signals can be decomposed to elementary signals. Thus, we can convert the analysis of any signals to the analysis of elementary signals. This is a principle of signal processing. The second reason is that the basic signals and basic operations can be served as good examples. They can help us understand the correspondence between the time analysis and the frequency domain analysis. We firstly will learn the elementary continuous time signal, including regular signals and singularity signals. Now, let's discuss what is the definition of regular signal. If the signal and its derivative do not have discontinuities, then this signal is a regular signal. Direct current signal is a common regular signal. Here is the definition, and this is the waveform. The DC signal has wide applications in the engineering, including the battery and DC source in the signal generator. Sine signal can be expressed using this formula. Here is a waveform. For the sine signals, the A represents the amplitude, omega sub 0 is the angular frequency, phi is the phase. The sine signal is a periodical signal. We can get the period t sub 0 equals 2 times pi over omega sub 0. And the frequency can be calculated as 1 over t sub 0. The relationship between the angular frequency and the frequency can be expressed using this formula. Here are two sine signals with different frequency. Now let's listen to these two sounds. Listening to these two sounds, we can conclude that for this signal, it has higher frequency. We can find that this signal breathes faster and has higher pitch. The next signal is the exponential signal. We first introduce the real exponential signal, expressed using this equation. Here is a waveform. We can find that when alpha is larger than 0, it is an increasing trend. When alpha is smaller than 0, it is a decreasing trend. The exponential signal can simulate the charging and discharging of a capacitor. In the charging stage, the voltage of the capacitor can be represented using this signal. At the discharging stage, the voltage of the capacitor can be represented using this signal. The imaginary exponential signal can be expressed using this equation. We can find that for this signal, its magnitude is equal to 1 and the phase equals to omega sub 0. The imaginary exponential signal is also a periodical signal. Using this equation, we can get its period. Thus, the fundamental period for this exponential signal can be calculated as 2 times pi over omega sub 0. We can find that it is the same as the sine signals with the same frequency. Now we learn the sine signal and the imaginary exponential signal. We can find that they can be linearly expressed. We can using the Euler's relation for this linear expression. Here is a cosine signal, and here is a sine signal. The Euler's relationship is proposed by Euler. He is a famous mathematician. The complex exponential signal can be expressed using this formula. Here S is a complex value, sigma is a real part, and omega sub 0 is the imaginary part. We can reformulate this signal as the following formula. And here we plot the imaginary part of this signal. We can find that the imaginary part of this signal is a non-answer amplitude sine signal. The complex exponential signal can simulate the vibration of a spring oscillator. Now let's give a summary. For the complex exponential signal, when its real part and the imaginary part are both not equal to 0, it is a non-answer amplitude sine signal. When the real part is equal to 0 and the imaginary part is not equal to 0, it is an imaginary exponential signal. When the real part is not equal to 0 and the imaginary part equals to 0, it is a real exponential signal. When the two parts are both equal to 0, it is a DC signal. Finally, we introduce the sixth signal. It can be defined as sin t over t. And here is a waveform. For these signals, it has some properties. When t is equal to 0, the value is equal to 1. When t is equal to k times pi, and the value is equal to 0. The integration of the signal equals to pi. That is to say, the area of this signal is equal to pi. Now, let's have a summary for this lecture. In this lecture, we introduce the regular CT signals, including the DC signal, sine signal, exponential signal, and sampling signal. You should master the definition and property of these signals. That's all. Thank you. See you next time.